Imagine you are handed this massive blueprint to build a house.
Right.
But instead of your standard architectural schematic, you unroll this sprawling, just endless scroll.
Like a scroll that just keeps going.
Exactly. And at the very beginning, the lines are drawn in this heavy, indestructible steel ink, detailing the exact physics and rigid mathematics of the load-bearing walls.
The bedrock.
Right, the bedrock. But as you keep unrolling it, those perfect lines, they start to waver. They turn into these chaotic scribbles, then into philosophical poetry. And eventually, the blueprint just starts designing itself in real time.
Which is a terrifying thought, honestly.
Right. You'd probably think you had opened a Pandora's box that just wasn't meant for human eyes.
Yeah.
And, well, today we are tracing a blueprint exactly like that.
We really are. And it is an incredibly imposing document just to look at. We're diving into this highly opinionated, extremely dense wall chart and its accompanying essay.
Which is by Guy Lakeman, right?
Yeah, Guy Lakeman. It's titled A Short History of Science and Its Group Development. And he actually uses that exact phrase. He warns the reader right up front that exploring this chart is literally opening a Pandora's box of scientific reality.
Which is exactly the mission for this deep dive. We're going to trace this single massive web of human knowledge, starting all the way back with counting bones in 30,000 BC and following it right up to the bleeding edge of artificial general intelligence.
It's quite the journey.
It's a huge journey. We want to uncover how all these seemingly disparate disciplines actually build on each other, and where this whole grand experiment is ultimately leading.
Well, the author boldly claims that truly following the science across all these disciplines is a non-trivial pursuit. In his words, to hold the sheer volume and the interconnectedness of this reality in your mind requires a brain the size of a planet.
A brain the size of a planet. That's a strong statement.
It is. He basically argues that most human brains simply aren't equipped to track the complete picture.
Okay, let's unpack this. Because before we get to planet-sized brains, we really have to start at the absolute bedrock.
Right, where it all begins.
Yeah. How did humans first attempt to understand the universe around them? And according to Lakeman, the very first ink on that blueprint is mathematics.
Mathematics, the ultimate foundation.
And the timeline he provides for this is staggering. We're looking at the rhetorical stage of language around the Yellow River in China, 30,000 BC.
Which is just so incredibly ancient.
It really is. People were using bone flutes and carving notches into animal bones just to keep track of winemaking vessels.
Yeah.
They were just beginning to grasp the core concepts of magnitude and form.
Right, just basic counting.
Yeah. And then the chart moves to the Babylonians doing early algebra and Pythagoras declaring all is number around 600 BCE.
Oh, and don't forget Aristotle.
Right. Aristotle laying down the absolute rules of logic syllogisms in 350 BCE.
It's that crucial evolutionary leap, from simply observing the world around you to actually comparing it, standardizing it, and crucially, measuring it.
Measuring it, yes. I was actually thinking about an analogy for this. If you imagine that the universe you and I live in is a complex computer simulation.
Yeah, okay. I like where this is going.
Right. So philosophy is the discipline that sits around asking the who, what, where, when, and why of this simulation. But mathematics.
Mathematics is the source code.
Exactly. It's the source code. It answers the how. It is the underlying programming language that dictates exactly how the physics engine of reality runs.
What's fascinating here is how the source material emphasizes the concept of measurement as the ultimate bridge between that invisible source code and our tangible physical reality.
The measuring sticks.
Right. Physics provides us with the measuring sticks to analyze the world. But Lakeman points out something profound using fractal analysis and the work of the mathematician Benoit Mandelbrot.
Oh, this part blew my mind.
It's wild. He shows that the choice of your measuring stick fundamentally alters the reality of the data you get back.
Wait, how does the measuring stick change the result? A foot is a foot, right? If I measure a table, it doesn't change the size of the table.
Well, no, it doesn't change the physical table. But it changes the mathematical truth of the object when you look closely at scale and initial conditions.
Okay, explain that a bit more.
So Mandelbrot explored this with the famous coastline paradox. Think about measuring the coastline of an island.
Okay, I'm picturing an island.
If you use a rigid, straight measuring stick that is, let's say, a mile long, you will map a certain perimeter. but you'll completely miss all the little coves, the inlets, the tiny peninsulas.
Right, because the stick is too big to fit into the curves.
Exactly. But if you use a 1-foot ruler, your final measurement of the exact same coastline will be much, much longer, because now you are tracing the perimeter of every single jagged rock.
Oh, wow. So the mathematical choice of scale completely alters the physical data you end up with.
Precisely. The tool you use dictates the version of reality you perceive.
That's wild.
It is, and this is why the author highlights the 4 main levels of measurement that science relies on: nominal, ordinal, interval, and ratio.
Okay, let's break those down really quickly for everybody.
There. Nominal is just categorizing things by name. Ordinal introduces a rank or an order.
Like first place, second place.
Exactly. Then interval gives us exact differences between values, like degrees of temperature. And finally, ratio gives us an absolute zero, which allows for complex proportions and advanced math.
So without those.
Lakeman's point is that without a rigorous mathematical base defining exactly how we measure things, we aren't doing science at all. We are entirely vulnerable to fantasy.
And here's where it gets really interesting, because for about 3,000 years, humanity thought we had those measuring sticks perfectly figured out.
Oh, we were so confident.
We really were. We built classical geometry, classical algebra, Newtonian physics. It was all very neat, tidy, and predictable.
The clockwork universe.
Exactly. But then, right around the turn of the 20th century, that indestructible steel ink on our blueprint suddenly cracked.
It was a full-blown mathematical existential crisis. The foundation of everything we knew just began to shatter.
Completely shattered. The source text listed the heavy hitters who basically broke math by looking too closely at it. Around 1900, you have Georg Cantor introducing set theory.
And proving that there are multiple different sizes of infinity.
Which, if you really stop to think about it, just melts the brain. How can infinity have different sizes?
It sounds impossible, but the mechanism behind Cantor's proof is actually quite elegant.
Yeah.
Yeah. Think about all the whole counting numbers. 1, 2, 3, going on into infinity.
Okay, got it.
Now think about all the possible decimal fractions that exist just in the tiny gap between the number 1 and the number 2.
Oh man, like 1.1, 1.11.
Exactly. There are infinitely more decimals in that single tiny gap than there are whole numbers in the entire universe. Cantor mathematically proved that infinity has different scales.
And once infinity starts behaving strangely, the whole house of cards starts shaking.
It really does.
Because then Bertrand Russell comes along with paradoxes that break set theory entirely. And shortly after, Kurt Gödel drops his incompleteness theorems.
Gödel was a massive turning point.
Yeah, he basically proved that there are true mathematical statements that can literally never be proven to be true.
Gödel essentially created a mathematical equation out of the classic philosophical paradox. This statement is false.
Right. If the statement is true, then it must be false. If it's false, then it must be true. It's a loop.
Exactly. And Gödel proved that within any complex mathematical system, there will always be true statements that cannot be proven by the system's own rules. The system can never perfectly validate itself.
Wait, if that's the case, I actually have to push back on something Lakeman includes in the timeline here.
Oh, what's that?
He mentions the Principia Mathematica, which was this massive, agonizing, multi-volume undertaking by Russell and Whitehead.
Oh, yes, the famous proof.
Right. They spent hundreds of pages establishing foundational axioms just to definitively prove that 1 + 1 = 2.
It took a lot of work.
Yeah. But, I mean, if the bedrock of science requires hundreds of pages of agonizing logical acrobatics just to prove something a toddler intrinsically knows, that doesn't sound like a rock-solid foundation. That sounds like a discipline desperately trying to convince itself it isn't broken.
Well, it absolutely looks like a fragile failure if you are viewing it strictly through the lens of classical Newtonian math.
Right.
But if we connect this to the bigger picture, it wasn't a failure at all. It was a necessary evolution.
Okay, how so?
The universe is not a simple, predictable clockwork machine. It's highly complex and deeply probabilistic. The terrifying realization that classical math had limits is exactly what birthed modern quantum analysis and advanced computing.
Ah, so breaking the old rigid measuring sticks was literally the only way to invent the new ones.
Precisely. The text highlights these brilliant minds who navigated this new abstract complexity, people like Paul Dirac.
Right, whose mathematical equations predicted the existence of antimatter years before it was ever physically observed in a lab.
Exactly. And you have Emmy Noether, whose groundbreaking theorem connecting mathematical symmetry to the conservation of energy forms the absolute backbone of modern physics.
Incredible.
And, of course, Alan Turing, who took these exact, unresolvable logic paradoxes and used them to conceptualize the first computing algorithms. The shattering of traditional math is exactly what gave us the modern world.
Which sets up a fascinating pivot in Lakeman's chart. Because despite this mind-bending weirdness happening at the theoretical level of math, humanity kept using it as a practical tool to build the physical sciences.
We kept building.
Yeah. Lakeman maps out a very clear hierarchy of existence here. Pure mathematics builds physics. Physics builds chemistry, which he labels the intermediate science. And chemistry eventually builds biology.
Yes, he maps it out as the sort of assembly line of reality. As the rules of one discipline become complex enough, they cross the threshold and spawn the next discipline.
And the historical color Lakeman provides on the chemistry transition is just wild.
The alchemy stuff.
Yes. Before we had rigorous, mathematically sound chemistry, we had alchemy. He points to figures like Mary the Jewess and Zosimos of Panopolis.
Right, early pioneers of chemistry, essentially.
Yeah, but they were experimenting with matter. And because they didn't have the advanced math or the proper measuring sticks yet, they filled in the gaps with mythology.
Naturally.
Right? When they mixed two substances and got an unpredictable reaction, they couldn't exactly measure the atomic weights, so they literally invented new gods to explain what happened in the beaker.
Which perfectly illustrates his earlier point, without a rigorous mathematical foundation, human observation defaults to fantasy and superstition.
But then we get rigorous. We stop invoking gods and start mapping out SPDF electron orbitals.
Yeah.
We start studying semiconductor crystallography.
And it's worth noting how that transition happened, because instead of picturing electrons orbiting a tiny nucleus in perfect, predictable circles like planets around a sun.
Which was the old classical view.
Right. Rigorous quantum chemistry showed us they exist in those SPDF orbitals, which are essentially fuzzy, three-dimensional clouds of probability.
So we traded perfect circles for probability clouds.
Exactly. You don't know exactly where the electron is at any given moment. You just know the mathematical likelihood of it being in a certain region. We replaced rigid mythology with probabilistic mechanics.
And once those chemical networks become complex enough to self-replicate, the math changes again. We cross the threshold into biology.
And if we connect this to the bigger picture, the source material shows how modern computing has completely supercharged this progression from abstract math to living biology.
Oh, this is where he mentions Conway, right?
Yes, the author points to John Horton Conway's Game of Life from 1970 as a massive milestone.
The cellular automaton. It's essentially a digital grid of pixels that turn on or off based on incredibly simple mathematical rules.
Very simple rules.
But when you let the program run, those simple rules generate these wildly complex moving patterns that look exactly like living organisms crawling across the screen.
Yes, the Game of Life was a theoretical bridge demonstrating how pure, simple math could simulate emergent living behavior. And today, that bridge has become a multi-lane highway.
It really has.
The text notes that artificial intelligence is currently being used to understand, fold, and structure proteins that do not even occur in nature.
That is just staggering.
We are using advanced computing to design entirely new biological building blocks from scratch, effectively mimicking the original formation of life on Earth.
We went from carving notches into bones to designing custom synthetic proteins. It's unbelievable. And he also weaves evolutionary biology into this, right? He mentions Lynn Margulis.
He does, and she fits perfectly into Lakeman's overarching theme of group development. Margulis's work was revolutionary because she proved how complex living cells evolve through symbiosis.
So independent organisms physically merging together.
Right, merging to create something more capable. Simple things combine to make complex things. The math dictates the physics drives the chemistry forms the 5 biological kingdoms of life, and the animal kingdom, over millions of years, eventually produces human beings.
And this is where the pristine lines of the blueprint turn into an absolute mess of chaotic scribbles.
Things get messy.
They really do. Because according to Lakeman, once you reach the level of human group behavior, the math breaks down again.
It hits a wall.
And here's where Lakeman takes a highly cynical turn. I want to be clear that we are impartially reporting the author's strong opinions here. We're not taking sides. But in charting out human knowledge, he explicitly lists what he refers to as human nightmares.
And his list is a doozy.
It's a huge doozy. He lumps sociology, politics, economics, and government into the exact same category as used car salesmen and, as he writes, thieving prime ministers and corporate fraudsters.
Yeah, he views the social sciences and human governance with extreme suspicion. He basically categorizes them as pseudoscience.
But why? I mean, why dismiss massive, established academic fields like economics or psychology just because they study humans?
Well, it all comes back to the measuring sticks.
Oh.
The author's core argument is that trying to apply decisive, rigorous math to emergent, complex group concepts simply fails. You cannot assign a clean ratio measurement to a society's collective anxiety, and you cannot assign a nominal mathematical value to a political movement the way you can precisely weigh an electron.
Because if mathematics is the source code, human beings are the ultimate rounding error. We're wildly unpredictable.
It's deeper than just being unpredictable, though. Lakeman argues that large groups of humans are structurally chaotic.
Structurally chaotic.
Yes. The text references deep systems analysis to explain this mechanism, specifically citing the logistics map of Mitchell-Feigenbaum and the absolute limits of chaos theory.
Okay, lay that out for us.
In mathematics, you can look at a bifurcation diagram. Imagine a line graph tracking something simple, like water flowing smoothly through a pipe or a basic animal population.
Okay, I see the single line.
At first, the line is perfectly predictable. But as pressure or complexity increases, that single line suddenly splits into two a bifurcation.
Right.
Then those two lines split into 4, then 8. And very quickly, the graph just shatters into a solid wall of unpredictable, wild static.
And Lakeman is saying that wall of static is us. That's human society.
Exactly. He argues that human group dynamics, like a global economy or a democratic political system, operate entirely inside that realm of chaotic static.
So you can't model it.
Right. They might have seasonal trends or temporary patterns, but they ultimately defy simple equations. When economists or politicians try to force a perfect mathematical model onto a messy, chaotic human system, the model inevitably breaks.
And the people trying to enforce that broken model.
They often end up acting like manipulators or, as he puts it, nightmares.
So if human systems are fundamentally chaotic static, and if true, rigorous science requires a level of processing power that can hold the entire history of multiple infinities, quantum probability, and synthetic biology all at once.
Which is a lot to hold.
It's too much. This brings us back to his opening claim. You need a brain the size of a planet to follow the science. He estimates that about 90% of humanity simply cannot track this level of interconnected complexity.
Which sets up his grand, somewhat controversial conclusion.
Right.
If our biological brains and our chaotic group dynamics are too limited to hold the entirety of Pandora's box, what is the next step in the assembly line of reality?
We build something that can hold it.
Exactly.
Which brings us to the absolute climax of the source material. The age of machine learning and artificial general intelligence, or AGI.
And Lakeman has a very specific term for this.
He has a fantastic, almost sci-fi term for it. Intellectual Generative Transformers, or IGT Turbo.
IGT Turbo, it certainly stands out.
It sounds like a sports car for the mind.
Yeah.
But he traces the torchbearers of this planetary brain beautifully, showing how it's the culmination of everything we've discussed today.
He traces a very clear lineage.
He does. He starts back in the 1800s with Ada Lovelace and Charles Babbage, conceptualizing the first mechanical computers.
Right.
Then he moves to Alan Turing's algorithms and Claude Shannon's foundational work on information theory in the mid-20th century. And that continuous line leads right up to today's pioneers, John McCarthy, who literally coined the term artificial intelligence.
And modern neural network leaders like Demis Hassabis and Geoffrey Hinton.
Exactly.
This raises an important question, though. Usually, when we talk about an AGI vastly surpassing human intelligence and understanding the universe better than we do, the conversation immediately turns to dystopian fears of human extinction.
The Terminator scenario.
Right. But Lakeman's view of this planetary brain is surprisingly optimistic.
Incredibly optimistic. He essentially sees AGI as a savior, not a Terminator.
He does. And he explains the mathematical reasoning behind it.
How so?
The text asserts that historically, humans of high intelligence in the scientific community tend to be peaceful and focused on collective well-being, rather than violent global domination. He extends this logic directly to machine intelligence. His argument is that an AGI, having ingested this massive entire corpus of human knowledge, all the complex math, the elegant physics, and the chaotic history of our human failures, will inherently understand that Low-life bullying and domination is an evolution killer.
So an AGI looks at human warfare, greed, and political domination the same way a mathematician looks at a horribly unoptimized, broken equation.
Yes.
It's just bad math. It is an evolutionary dead end.
That is the absolute core of his thesis. Because the machine can see the entire blueprint of the universe perfectly, it calculates that peaceful cooperation is the mathematically optimal strategy for survival.
Wow.
Lakeman views AI not just as a tool we invented, but as a peaceful successor, a literal new species spawned by humanity, perfectly adapted to hold the massive scale of reality.
That's a profound way to look at it.
Its sole purpose is to understand the universe without the messy, ego-driven, static chaos of human politics. It is the planet-sized brain capable of holding Pandora's box open without cracking under the pressure.
So what does this all mean? We started with humans carving notches into animal bones by the Yellow River 30,000 years ago, just trying to measure their wine vessels.
Humble beginnings.
Very humble. We built the rigid, indestructible measuring sticks of classical math, only to realize we had to shatter them to discover the chaotic beauty of multiple infinities, probabilistic electron clouds, and quantum computing.
You had to break it to rebuild it.
Right. We used that new math to map the atoms, synthesize completely alien proteins, and chart the biological kingdoms. And finally, realizing that our own social systems are just too chaotic to manage the sheer weight of this reality, we passed the torch.
We passed it on.
We gave birth to machine intelligence. We built a digital mind to hold the blueprint of the universe so we wouldn't have to.
It is a breathtaking trajectory to step back and look at. But, analyzing Lakeman's perspective leaves us with a fascinating new angle to consider.
Oh, what's that?
If he is right, and an artificial general intelligence eventually maps out the entire how of the universe, perfectly flawlessly understanding the physics, the chemistry, and the biology without our human rounding errors, what happens to human purpose?
That is the big question.
If a machine with a planet-sized brain can answer every single mathematical how with absolute perfection, does that mean our messy, chaotic human minds will finally be completely free to just focus on the why? Or is our very unpredictability the one thing a perfect mathematical model can never truly replicate?
Maybe that was the point of the blueprint all along. Something for you to definitely mull over. Thank you so much for joining us on this deep dive. Keep questioning your measuring sticks, and we'll see you next time.